Hello, welcome to the Sunday review for I think it's week 13. Sorry that this one is held completely asynchronously. I know I'm going to be traveling. I assume many of you will be traveling. Thanksgiving is upon us. It's almost time to see family. And the school year is almost over. So, these are good times, yet we must continue our study of computer science. So today's topic is going to be graph traversal. So at this point in the course, hopefully you have some kind of grasp on what a graph is, right? A graph is a data structure that is similar to a tree and it's similar to a linked list. And that data is stored in a node, and that node has pointers to other nodes, and it forms kind of this, interconnected network of nodes that have data, and the nodes point to other nodes, and so on and so forth. Whereas in a linked list and then in a tree, we see that there are some very strict rules for how nodes can be connected to each other. Within graphs, we kind of take away those rules so that we can model more complicated problems. And I think graphs are really cool for that reason. Like, they are very useful. If you plan to do anything with computer science or mathematics for the rest of your life, this is a topic that you will continue to be thankful that you understood it if you do, really put in the work. Okay, so without further ado, let's talk about BFS and DFS. So these are, not the only two, but these are like the OG graph traversal algorithms that every programmer has got to have in their back pocket. The first of which is BFS. As you can see, BFS stands for breadth first search. So given a graph, and this right here is an example of a graph. As you can see, we have nodes that are connected to each other somehow. BFS is an algorithm that, starting at some point in the graph and using a queue, you search the entire graph looking at adjacent nodes first. So essentially, you look at surrounding nodes before you make it to the very end of the structure. And we're going to see this in this animation. So assuming we're doing a breadth first search on this graph, we start at node 2. As you can see, there's a red circle drawn around 2 to indicate that that's order 0, or all of the nodes that are available within 0 connections. The blue circle now represents all of the nodes that can be discovered within 1 connection. And then the yellow circle represents all of the nodes that can be seen within 2 connections. And as you can see, breadth first traversal is going to be an interesting way to traverse a graph structure. So imagine we have like a social network, right? And you want to find maybe a friend of a friend, a mutual friend. Well, a good way to do that would be a breadth first search algorithm, where first you look at, maybe this is the user, and then this is all of the user's friends, and then this is all of the friends of the user's friends. And as you can see, imagine we've got a user 2 and a user 7. Found a path from 2 to 7 and 2 connections. And so while shortest path algorithms are a topic of their own, and we'll cover that next week, this is just some motivation. BFS is very friendly, I think very easy to stomach. I'm going to play the animation again. So you just start from any node. As you can see, we just draw concentric circles, and that's BFS. So not super bad. And as you can see on the left, we actually draw out a tree of what the nodes appeared to us in the order that we discovered them, right? So you can see we started with 2, and then on this next level are all of the nodes that we were able to find with 1 connection, and then on the second level are all of the nodes that we found in 2 connections. And as you can see, we can trace any of these paths, like for instance 2, 6, 5, 2, 6, 5 gives us a valid path that was on the graph. So we took this graph, we traversed it, and it gave us a tree, which is kind of cool. And we're going to see more properties of this later. But in summary, in an unweighted graph, breadth first search is useful for finding shortest paths from a single source. This algorithm is done using a queue, and when we get into the drawing portion, I'll explain this more thoroughly. It has a running time depending on how the graph is represented, and again, I will explain this in a second, where V is the number of vertices, E is the number of edges. Don't worry about that just yet. Okay, so depth first search, kind of like the cousin of breadth first search, the other OG traversal algorithm, if we're thinking before that breadth first search, you want to look at all of the immediate like neighboring nodes of an input path before you get to the end of the structure. DFS is the exact opposite. So essentially the paradigm here is you want to find the deepest path possible first. So I guess there's no animation, so I'll just have to draw this. But imagine we were to do DFS starting at, node 0, for instance. Looking at this node 0, we have a path to 5 and a path to 1. So imagine I arbitrarily just say, okay, well, I'm gonna search here. So you would go 0 to 5, and instead of then traversing 1 and drawing that concentric circle like we had before, you just keep traversing, not looking backwards, until you get as deep as you can possibly get. So 0 would go to 5, 5 would go to 4, 4 would go to 3, 3 would go to 1, 1 would go to 2. And without having to worry about, the concentric circles or looking at all of the nodes that 0 points to, we very quickly find this very deep path. Hence the name depth first search. So depth first search has its own number of uses. Again, this is going to come up in later reviews. Intuitively, it's just good to understand this as a building block. It's very helpful for many programs. And like we had with, I don't believe, okay, there's no animation, but like we had a graph over here, and we ran breadth first search traversal on this graph, and it gave us a tree that represents the exploration. If we run depth first search on a graph, it also is going to output a tree that represents the order in which we discover the nodes. And those nodes in the tree, which again, I'm going to draw this, so don't worry if you can't visualize it yet, but the edges that build the tree for DFS are actually they're going to be classified into one of these 4 categories, depending on the order in which we saw them and the way that they're connected. So we'll talk about this in a minute. See, the slide says to draw. I'm going to, not because they told me to. Okay, so before we get into the actual note-taking section, just some summary. So DFS is useful for many things, including detecting cycles, topological sorting, connected components. We'll worry about these next week. DFS has the same running time as BFS, different algorithm, but same complexity. You can think BFS is a queue-based implementation, whereas DFS is a stack-based implementation. And when we run DFS, we're going to classify edges into a few different categories. So I think that about sums up the intuitive, high-level, memorize all of these buzzwords portion of the Sunday review. Now it's time to get into the good stuff, where I'm actually going to prove some of this stuff and draw it. So let me go ahead and share my iPad. Okay, so hopefully this can be seen. Otherwise, I apologize sincerely. But so I've already drawn this graph here. Just as a nice little, this example is actually quite pretty. I picked it on purpose because this graph contains all of the 4 different types of edges that we were talking about before. So it should be very useful for making some points. Imagine we're given this graph and we're asked to do a breadth first traversal. Well, before we get into any of the actual algorithms or the math, we remember that imagine starting at node A, and this is just a random choice, right? We could do a breadth first traversal starting from any node, hypothetically, but imagine starting at A. All we need to do breadth first traversal, like at least in our heads intuitively, is to draw these concentric rings that describe which nodes we can find within 0 paths. This would be like 0 paths. This is 1 path. The next ring would be within 2 paths. You can see that would be like this. And then just, it's kind of out of bounds. And then finally within 3 paths, like so. And I don't think that's so hard to understand. Maybe it's a little bit difficult to, in your head, think about how does this in any way relate to a queue-based traversal. So, let me actually explain that. So for BFS, when I said this algorithm uses a queue to traverse, I'm just going to be cheeky down here and just kind of like represent the queue. But imagine every time we encounter a node, we add its children to a certain data structure. Well, if we add the children of the node that we just encountered to a queue, we're doing BFS. So it's going to use a queue. If we add the children of the node we just encountered to a stack, that's DFS. And that is literally the only difference between these two, is the data structure that we use to store the nodes of the children. So yeah, let's go ahead and do a BFS traversal. So like I said, first thing we're going to do is we're going to look at A. So imagine A is on this queue, and we're going to push all of A's children to the queue. So that's going to look like this. It's going to look at A, B, C. And now that we've visited A, we can go ahead and like mark it out. Or actually, you know, maybe it would be more descriptive if I labeled this as like, you can see this in 0 iterations. Okay, so now we're going to imagine we've like popped this from the queue. Now we're looking at B, so we're going to add all of B's children, which in this case is just C, and we're going to add all of D's children. Did I mess up? Oh, I did mess up. I'm so sorry. I'm so prone to error. Forgive me, please. Okay, so for anyone who's paying attention, A was first in the queue, and the next in the queue was B and D, not C. Sorry, my bad. So assuming that we pop A from the queue, we're now looking at B and D, so we're going to add B's children, which is C. We're going to add D's children, which in this case is just E. Pop these two, and at this point we've found this much, and then we're going to, C has no children, so popping it is easy. E has F, and then C is our last concentric ring. And we pop F. So again, don't worry about this too much. The point of this week is to build intuition. So that's BFS. I think it's relatively pretty straightforward. Okay, now let's think about DFS. So what if we were doing exactly what we just did, but we did it with a stack instead? So for DFS, let's put some kind of stack over here. And you know, maybe a stack is again not the most descriptive thing. Let me say like nodes to visit, and just know that this is a stack. So the first thing is going to be A that we visit, and then let's just randomly pick this path first. So A is going to see B, and then we're going to add B's children to the stack. So that's going to be C, which is like this. C has no children, so we can pop it off the stack. Do like so. B has no children, so we're going to pop it off the stack like so. A is not finished yet, so we've still got to find D. And then D is going to let us find E. And see, E is going to let us find F. And then F has no children. E has no more nodes that we need to find. D has no more nodes that we need to find. And A is good. So essentially, again, I don't want anyone to memorize that, or at least not yet. BFS is traversal with a queue, and DFS is traversal with a stack. So let's do that again, but let's focus a little bit harder on what's actually happening. So imagine we're doing DFS, and we're starting at node A. I'm going to mark that actually with a 0 to indicate that we have just started traversing. And let's go ahead and randomly walk this direction. So I'm going to use these numbers to represent the steps that I take in this traversal. So A goes to B, B goes to C. As we can see, I'm going to use 2 to mark the case that this is the second step that I've taken. In convention for marking a DFS path, it's common that we complete this little slash notation when we do a turnaround, right? So C has no more remaining children, right? It's just empty space over here. And when we get to this case, we turn around and go backwards, essentially. So we're going to walk back on the path like so. Now we're looking back at A again. And before we're ready to close out A, right, we can't just say 5 here because we still have nodes that need to be visited on this side of the graph, right? So next we're going to visit D, and let's mark this with a 5 and open slash. We need to see E, call this a 6. Need to see F, call this a 7. F has no children, turn around here, and we turn around here. So this is DFS by hand. I think this explanation makes more sense than the stack and queue thing. So hopefully you're not too fried from that. Okay, so some quick notes about what happened here. So if it seems like I just ignored some edges or I made some rash decisions that I didn't explain, this is true. This is in fact the case. Because what about this node? I mean, not node. What about that edge, right? What about this edge? And what about this edge? Why did I seem to just skip those? Well, when we're doing DFS, the idea is that we're discovering unique nodes, right? So when we were walking along the path for the first time this way, B was undiscovered, so we added it to the path, and C was undiscovered. When we backtrack back this way, back to A, we don't need to consider this edge to C because we've already seen C, right? C is already discovered. So this edge, rather than being one of these red edges that we used to mark the discovery, this is going to be one of our special type of edges that I kind of hinted at earlier. And I'll talk about this in a second. And then so skipping this edge, we kind of just randomly went this way because D was the next child that we had to visit. And then we went this way again. And so here at a crossroads, we didn't go back to A because A is already discovered. We didn't go back to C, right? Because C is already discovered. Instead, we went to F, right? And then we had to backtrack this way back till we got to where we started from. So to answer the question of what do these edges mean, well, enough beating around the bush. I'm going to actually answer it. So the red edges mark the nodes as they're being discovered, and these are called tree edges. And in fact, if we are to they're called tree edges because before, if you remember, the tree that was made from the DFS traversal, that's why they're called tree edges. So starting at A, the first thing we did was we discovered B, right? And then from B, we discovered C. Hopefully you can see where I'm going with this. C had no children, so we turned around. B had no children, so we turned around. From A, we then discovered D. From D, we discovered E. And from E, we discover F. Okay, I think this is right. And again, y'all, I'm so prone to error. So if I made a mistake in here, don't get hung up on it forever. But I believe this was the order that things happen, right? So if we're to draw this, we're here, 0, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, okay, so that seems legit. That seems like the order that we conducted the search in. Okay, so the first type of edge, and here, let me actually, I'm gonna color code this in a second. So the first type of edge that we've got is known as the tree edge. So tree, I'm gonna move this tree down so that I have more room. Okay, so the first type of edge that we see is called the tree edge. So tree edge. And you can think of the tree edge as kind of marking discovery, right? This kind of represents the order in which we saw the nodes and discovered them for the first time. So what about this one? What about this edge right here from A to C? Well, let's add this to our tree down here. So an edge from A to C would look like this on our tree, right? And this is markedly different than all of the other edges on our tree, right? Because now we have, right, all of these red edges, follow the binary tree properties, right? Each each node, well, it could potentially be a ternary tree or however many nodes, but as you can see, there are no skips. This blue one, this is a skip, right? This is a skip edge. So we're going to call this a forward edge. Forward edge. So that's two of the possible types of edges. Let's see, what else happened? Let me move this a little bit more to the center. So the next type of edge that we just ignored was this one, from E to A. What? And so let's draw that on this tree. So from E pointing back to A, this is a back edge. So as we can see, whereas the red nodes follow a very neat path, the blue node skips forward in the tree, a back edge skips backward in the DFS tree. Yeah, pretty self-explanatory, I think. And then the last type of node that we ignored was this one, from E to C, from one discovered node to another discovered node that it is not like related to, and that was from E to C. So that was from here to here, and this is called a cross edge. So hopefully, by now, you should have some confidence when it comes to these types of edges, how to do DFS with these strange or seemingly strange numbers mean. For the sake of argument, let's just practice these a few more times. So let's just add in some edges to this graph. So let's imagine A connects to C. Let's imagine A also connects to F. And in fact, this would happen to be a forward edge, right? Because we are skipping forward in the graph to something that we've seen before. So A connecting to F. This is another forward edge. Let's draw another back edge. So let's imagine, for instance, D points back to A. Well, this is going to be a back edge, right? D pointing back to A. Let's put another one in the tree. Say, imagine F pointing to D, for instance. We might get a little silly. We might say that F points to D. And in that case, see, F pointing to D would look like this. And let's get even more silly, and let's add some cross edges. So what if F pointed to C? Well, this is a cross edge, right? So F pointing to C, it's a cross edge. Let's imagine, what if B pointed to E? Maybe this is an obnoxious way to make this point so many times, B pointing to E. So you can see that's a cross edge. So depending on how the different elements are discovered in the DFS traversal, and again, this does it is a stochastic process. It depends on the order in which you find nodes. The rest of the connections are labeled accordingly, and this is DFS. So I think DFS is significantly more difficult than BFS. This is depth first search, but it's still reasonable. Important to know. It's good stuff. I guess also one last thing that I think is probably worth note. So let me draw the graph that we had before. I think it looked something like this. I think A pointed to these nodes, and then we had D and E. I think E pointed back into C, and also to F. No, I think. Was that how I had it? Yeah, okay. So imagine we've got this graph. There are kind of two different ways to represent this graph algorithmically. So the first of which is going to be the adjacency matrix. And I think this is the most intuitive one, right? Like you just describe every possible pair of combinations between every possible node. So if we were to list all the nodes, so A, B, C, D, E, F, and then once again, A, B, D, no. And I'm so prone to error, y'all. I'm so sorry. A, B, C, D, E, F. Let's extend this a little bit. Essentially, this adjacency matrix will just mark either a yes or a no about whether the edges are connected, right? So let's actually be consistent and let's actually mark these things for real. So let's see. So A is connected to B and A is connected to D. So in our adjacency matrix, we would say we'd put a 1 here and a 1 here, and the rest are zeros. And then we just repeat this process. So B is connected to C, and that's it. And then let's see, C is connected to nothing, where 0 means no connection between two nodes and 1 means a connection. D is connected to E, I think was the only one. Yeah. I hope I'm getting this right, y'all. If I mess this up, again, don't get hung up. Let's see. So E is connected to A, C, and F. A, C, and F. And then F is connected to nothing. So this is the adjacency matrix. And this information can actually be summarized in a more efficient and compact structure known as the adjacency list, whereas we represent all of our nodes in a similar way, so A, B, C, D, E, F, except this time we have each of these nodes here on the left you can think of as like a sentinel node in a linked list that contains all of the connections. So we can actually go ahead and just translate from the matrix to the list. So looking at this first row here, A is going to point to B and D, B points to C, C points to nothing, D points to E, E points to A, C, and F, and then F is going to point to nothing. So this is the adjacency matrix, and this is the adjacency list. Okay, and so the reason I bring these things up on top of this quite colorful picture that I drew before is that when we're thinking about like what is the time complexity of constructing this DFS tree and doing these operations, well, it kind of depends on how the information is presented to us. So if we're looking at doing DFS on an adjacency matrix, as you might be able to intuitively see, well, we've got to perform, you know, this many searches, right? And this number is going to be the number of vertices here and the number of vertices here. So doing DFS or BFS, I'm just going to write that. So BFS/DFS is going to be this expensive, right? As you can see, just geometrically, this is true. Whereas if we are doing DFS or BFS and the information is encoded in this list, well, we're going to have to at least traverse this spine right here, which this is V. And then also we have to traverse all of the possible edges, and we're going to call this E. And so this is going to be BFS/DFS of O of V plus E. Not super complicated. Don't get freaked out when you see this formula, especially. Just think it's kind of important to know. Yeah, so that's, that is a really thorough look at depth first search and breadth first search. I hope this clears up some confusion if there was any. Hopefully it gives you a good foundation to think about these things. I mean, there's different properties about these different ways of describing information that I think are kind of cool, maybe worth one little pass before we do our summary. So if we're given an adjacency matrix, there are some properties of this, right? So as in each row represents the nodes that you can reach from A, right? So A can reach B, it can't reach C, it can reach D, it can't reach E, so on and so forth. If we actually flip this and look at the columns, a column tells you the nodes that can reach a node. So kind of the opposite direction. So this says B can be reached by A and nothing else, which in our graph, B can be reached by A and nothing else seems to be the case. Or let's take another example. Let's look at C. So C can be reached by, according to this, B and E. So C can be reached by B and E. Seems legit. Yeah, just thought I'd point that out. So in summary, what we've seen so far is BFS and DFS are just different ways of traversing a graph. Pretty intuitive. I think they're pretty straightforward. They both create a traversal tree, and that tree is going to be different depending on the order in which you found the nodes. For BFS, you can actually classify those different nodes into these 4 different categories, and you can represent the information that you found in the graph in 2 different ways, which lead to 2 different runtimes for the traversals. So hopefully you'll find that information useful. Stop share. So if y'all have any questions, please feel free to reach out to me. I will be available by email. I hope y'all have safe travels and a wonderful Thanksgiving. Yes, take care of yourselves. I will see y'all back in class soon.